Hi everybody, welcome. I'll take off my mask as soon as, okay, I'll take it off right now. How are you doing? Enjoying reInvent this year? It's so exciting to be here in person. My name is Prarthana Karmakar and I'm a software development manager in AWS. In this session today, I also have Mark with me.
Hey, I'm Mark Olson. I am a senior principal engineer in EBS, and I've been around for about 10 years.
So we have been thinking about storage and virtualization here in AWS and EBS for several years now. And today we are going to talk a little bit about block storage. I think it's very loud. Thank you. It's booming. It's okay. Yeah. So we will be talking about block storage today and dive a little bit deeper into Block Express architecture and our new SAN in the cloud offering. But before we get started, I wanted to talk about where EBS fits into the AWS storage portfolio. AWS offers three main types of storage: object, block, and file. Now we also offer a range of options for backup storage. These solutions are designed to provide cloud scale, secure storage, but with a different interfaces to meet the needs of your applications. In this session, we are talking about block storage, as I mentioned. Block storage is found in all kinds of computers and mobile devices. Practically anything that has a hard drive or a SSD drive where you can write data, usually in a file system, to keep everything organized. However, the block storage differs from object and file in that it does not depend on the metadata for the storage or retrieval, which makes the reads and the writes really fast. For EC2 instances, you have the choice of using a local instance store or EBS. Now, what I mean by local instance is the raw disk that can be attached to your EC2 instance. That is in your EC2 instance, but it is protected by our Nitro controllers. Now, what is EBS? Amazon Elastic Block Store is a block level storage that can be attached to Amazon EC2 instances. As I mentioned before, instance storage is raw disk, while EBS is a large distributed system that provides high performance, is highly available and highly durable, and it can be attached over the network to your EC2 instance and is designed for most workloads at any scale. The most important thing to remember is that an EBS block device, or EBS volumes like we call it, is not just a raw disk. And you will see in a bit that we have built EBS in a way that makes it possible for us to provide a constant new features and a stream of innovations that we drive here. Now, when you have an EBS volume, what can you do with it? EBS volumes can be attached to an EC2 instance in the same availability zone, and it appears in your instance just like any other disk. You can create a file system, or you can write on your write on the EBS volume from your EC2 instance, and the storage can be persistent, which makes the data, which stores the data even if you disconnect it from your instance. In terms of performance characteristics, EBS volumes matches the characteristics of your local storage, whether it is a hard drive or SSD drives. And within those families in EBS, we provide a range of options for different volume types with different performance, price, and durability characteristics, which is designed to match the needs of your applications that you run in AWS today. All management of EBS, including lifecycle features like creating a volume, deleting a volume, or even changing a storage type or the performance characteristics, is available to you online via all the tools that you are very familiar and comfortable with, whether it is the AWS SDK, the APIs, or the AWS console. And with all volumes, you can take a point-in-time snapshot for retention and recovery. Now, we launched EBS 13 years ago in 2008. And today, it is used by millions of developers to store exabyte of data across millions of EBS volumes, driving trillions of IOs every single day. In that time, in this 13 years, we have come to understand what our customers care about most, about using the block storage in the cloud. We found that the customers care a lot about high performance for their most resource-intensive applications. This means high IOPS and throughput. So we built a volume like IO2, which is built to scale to 64,000 IOPS and 1,000 megabyte per second of throughput. Customers also care a lot that their IO needs to be very fast and consistent. So our SSD volumes like GP2, GP3, IO1, and IO2 are built to deliver average single-digit millisecond latency, while our new Block Express architecture and the new IO2 Block Express volume type provides sub-millisecond latency. We also found that reliability is very important to our customers. Customers care and they want their data when they want it, and they also want their data to be safe. So EBS provides 99.999% of availability, that's 5 nines availability, and annual failure rate as low as 0.001% for a IO2 volume. Now, customers also want their block storage to grow as their applications and their usage grows, whether second over second or year over year. Individual EBS volume scales from a single gigabyte to up to 64 terabytes. And you can have petabytes of total storage, supporting everything from massive enterprise-level databases to pods of hundreds of stateful containers. Tools like Elastic Volumes allow you to switch between the volume types. You can increase your storage, find the right size performance, making EBS very easy to manage and scale with your business. Other tools like EBS Data Lifecycle Manager allows you to set up the backup schedules or retention policies for your volumes. Of course, your data must be secure. EBS enables AES 256 data encryption, and that is as simple as checking off a box, or as complex as self-managed KMS keys. Now, EBS encryption has no impact to performance. So there is no reason really that you should not enable it for your volume types. In fact, with just checking off a box, you can enable it for all new volumes that you create in your account. And like all AWS services, customers push EBS to provide all of these great functionalities and features at an absolute best value for their money. And with cost-effective pricing, EBS has done just that. We found that these are the 6 areas that our customers care about most. So in EBS, we drive most of our innovations in these 6 areas, in these 6 buckets. You can see that focus in the functionalities, capabilities, and features that we have built over the last year since we launched. Back then, we offered only one volume type and the ability to take the snapshot of that volume to S3 for backup. That first volume type, which we now call standard, was backed by hard disk drives, and it offered up to 1 terabyte of total storage with no performance guarantees. Since then, we have expanded our volume offerings quite a lot. The provisioned IOPS IO1 volume was our first SSD volume. Then came a lower cost SSD option, GP2. And now we have GP3, which comes at even lower cost and better performance. We also build the lower cost hard drive volumes, SC1, for cold streaming products, and ST1, which is our higher throughput streaming volume, for higher throughput streaming workloads. And of course, with our most recent launch, IO2, offering higher IOPS per gigabyte and lower annual failure rate than any other volume type, than any other EBS volumes. And on these volumes, we have continued to innovate across all these 6 areas that I called out previously that our customers care about most. I can't cram all 30 years of functionalities that we built in this one single slide, but I do want to call out Elastic Volume, Data Lifecycle Manager, Encrypted Volumes, and many such new features and functionalities that we built, which continues to provide a steady stream of innovation, helping our customers with their block storage every single day. Now, these volumes are good for a large number of workloads. You all have different types of workloads. So I'm going to walk you through a few broad categories that will help you understand where your workload might fit. And not only that, you will also be able to recognize that not all workloads fit into these nice and neat little boxes. So EBS allows you to pick and choose. And I will walk you through exactly how to do that. So EBS has 2 main families of volume types today. We have our SSD back products and we have our hard drive back products. On the SSD side, we have GP3, which is our general purpose volume, and our IO2 volumes, which runs on EBS Block Express architecture. And then on our hard drive side, we have our SC1 and ST1. Now, which one do you choose? Now, let's start with database workloads. This is a lot of what we see. Most applications have some sort of data store behind them. This is typically where your performance requirements also come into play. Most databases, whether it is SQL-based or NoSQL-based, have a write-ahead log or a journal, which is sequential. And the real application pattern, however, is highly workload dependent. What that means is that how your customers are using your applications or your database drives the requirements of your databases. Typically, we see that the customers have the best experience with our SSD volumes here. But sometimes our hard drive back products also work. Now, let's dive a little deeper into the SSD back product. I start with GP3. This is a volume type where we spent a lot of our time with, analyzing pattern, analyzing the workloads, analyzing what your performance requirements are to achieve a truly performance sweet spot for most workloads, about 70 to 80% of the workloads. GP3 satisfies nearly most of the workloads, and it is designed to be a truly general purpose volume. And that is actually why we also call it the general purpose volume. So if you don't know which volume type to start out with, I highly recommend you start with GP3. You also have the ability to provision more IOPS and more throughput when you need it without being dependent on the storage size. GP3 is designed to provide a predictable 3000 IOPS baseline performance and 128 megabytes per second of throughput, and regardless of the volume size. However, if you need higher performance, you can scale up to 16,000 IOPS and 1000 megabytes per second for an additional fee. You can provision these volumes from 1 gigabyte all the way up to 16 terabyte. A single digit millisecond latency for which GP3 provides, that's why fits most of your latency sensitive interactive applications, your boot volumes, your bursty databases, your dev test environments, anything actually. Continuing with the pace of innovation, last month we announced the general availability of our Block Express IO to Block Express volume type. We have been working for several years now on a series of foundational changes in EBS. This include building a new storage fabric backed by our SRD networking protocol, optimizing our instance data path with Nitro, and completely rethinking our hardware design. The result of that hard work is what I'm referring to as the architecture of Block Express. IO to Block Express volumes offer 4 times the performance of IO1, up to 256,000 IOPS, 4,000 megabytes per second of throughput, and you can provision up to 4 times more storage than IO1, up to 64 terabytes. And perhaps most important for your demanding applications, it will offer this high performance numbers at an average sub-millisecond latency. Now, what exactly do I mean by your demanding applications or mission critical applications? If you answered yes to the question in the previous slide, then your applications are mission critical, demanding, tier 1, or they are not. Now, let's go into one other type of workload, which is media. This is your rendering farms, transcoding, encoding, any sort of streaming product. Here you typically have a higher throughput requirement, mostly sequential, pretty sustained, especially when you have a pretty sustained and substantial rendered jobs. For this kind of workloads, our throughput optimized hard drive back product might be a ST1, might be a very good fit. Now, ST1 is a throughput provision volume type. The baseline performance scales with the size of the volume. Here, instead of measuring in IOPS, we are talking about throughput in megabytes per second. Baseline is 40 megabytes per second per terabyte provisioned, up to 500 megabytes per second. The burst is designed to allow you to scan the entire LBA range a few times a day. You get that up to 500 megabytes per second. These are not designed for boot volumes, and you have a minimum capacity of 125 gigabytes, but you can go up to 16 terabytes. And on the logical merge, now what I mean by the logical merge is that we don't actually hold on to your IO and wait for the next one to come in before we complete it. We just keep track of it, and if the next one looks like it was in the same place or sequential or the next LBA range over, then we count it as your previous IO. These are very good for large block, high throughput, sequential workloads. Now, data analytics is another common workload. You have got log analytics that you want to do, Kafka, Splunk, Hadoop, or maybe data warehousing, different kinds of data access patterns. Typically, these are high throughput requirement, usually sequential IO, but not really sustained applications. There might be some hourly, daily, or even weekly periodicity to it. These are good for our hard drive products, either SC1 or ST1. Now, SC1 is a little bit more colder. Similar to our ST1 volume type, the performance of SC1 is just a little bit more modest. This is designed for one complete scan a day. So the baseline throughput is lower, the burst throughput is lower, and it comes at a lower cost. So what is happening here is you're trading performance with cost. Everything else is very similar to our ST1 product. So you got the 1 MB logical merge and the capacity range from 125 gigabyte to 16 terabytes. These are ideal for large sequential workload, but something where you're not doing multiple full volume scans a day. Use cases includes sequential workloads like logging and backup. Now, file sharing is also another common workload. This could be a web server or things like CIFS, NFS, or this could even be your nearline archive. Oftentimes, these are super low throughput, very bursty, unpredictable. But when they do happen, there is often not a lot of traffic that goes on. And you are designing this with cost sensitivity in mind. So for this kind of workloads, our SC1 product is super compelling. EBS allows you to mix and match your volume types. You can take an instance and you can attach any number of volumes to your instance, any shape, any size, or performance characteristics, and really fine-tune what your application requirements are. You can use elastic volume to change your volume types, add or modify performance characteristics, and just adjust it according to what your application requirements are at that point of time. With the inclusion of IO2 Block Express, you can see that the performance curve has extended quite a lot from before. Now let's dive a little deeper into that. EBS scales as your applications grow, and you only pay for what you use without any long-term commitments. So now you can start moving those applications that you have in your data center into AWS and start applying the benefits of cloud economics, even where your performance requirements are the highest. When your application or data needs change, you can easily modify the performance or storage type. EBS SAN in the cloud performance is now on par with your on-prem mid-range SAN, but you don't have to manage or buy that SAN. You get all of that performance just by moving your workloads into AWS. You also don't have to manage the complex infrastructure that often comes with owning a SAN. Also, with AWS's constant innovation, you don't have to go through a constant hardware refresh cycles just to get the performance benefits or the new features and functionalities that we are adding. Actually, I'll invite Mark to come and take us through this in details.
Thanks, Prathana. So earlier, Prathana mentioned 6 different categories that our customers have told us are super interesting to them. We're going to dive a little bit deeper into 3 of those, 3 that I actually care a lot about. We'll start out with reliability. So the EBS SAN in the cloud architecture offers reliability for mission-critical applications. Each IO2 volume is designed to protect against failures by replicating within the availability zone, offering 5 nines of durability, or availability, and an annual failure rate of 0.001%, which is 5 nines of durability. For simple and robust backup, you can also use EBS snapshots. And when you combine it with Data Lifecycle Manager, which is a product that allows you to create schedules that will automate your snapshot management. So we think of reliability, volume reliability, in 2 ways. First, we think about availability. Availability is uptime, or the heartbeat of the service. Is the service running? Can you access your data? Typically, it accounts for our infrastructure, but it also accounts for the APIs that allow you to manage the lifecycle of your storage. So that's create volume, create snapshots, attach it to an instance, maybe detach it and attach it to a different instance. EBS is designed to deliver 5 nines of availability to our customers. And now, if we design for 5 nines, we wouldn't actually deliver that. So our internal design goals are much higher. We constantly track that, and we've got alarms so that even if we don't get close, and so even if we do start to get close, we're able to reconcile it to make sure that we continue to deliver that 5 nines of availability. The second thing we think about is durability, or our ability to keep your data safe. EBS has up to 5 nines of durability. This is significantly more than a typical disk. Whether it's an SSD or a hard drive, if you've got a disk, it's typically got a failure rate of 2 to 4% per year. And the way that you can think about a failure rate of 5 nines, a durability of 5 nines, is that if you have 100,000 volumes, on average, one of those will fail every year. So let's dive into under the hood of how we have architected and evolved our control plane design to make sure that we achieve the availability. What do I mean by control plane and data plane? EBS is a distributed system. It's actually multiple distributed systems, as we'll get into in a little bit. But with distributed systems, we typically think of the data plane, which is the thing that is actually doing the actions that you require. So in the case of EBS, it's storing your data. This accounts for the EC2 instance, the Nitro controller that's in the EC2 host, our storage fabric, the storage servers, et cetera. That's all part of our data plane. And so if you've got a data plane, you have to have something to manage it. And that's what we call our control plane. 13 years ago, in 2008, EBS began its journey with a single monolithic control plane. This control plane was responsible for all volumes in a region. Now, we're really creative, and so we called this Storage Manager. As we explored our architecture and kind of evolved and learned how customers scale and learned how we can scale, we recognized that having the availability of an existing volume is pretty important to our customers. And having a regional point of failure was not really a good thing. So we took the first step towards a smaller blast radius, and we created a new service called the Configuration Manager. So the Configuration Manager is responsible for storing the map of the volume to the storage servers that it's on. And it's critical to how EBS volumes are attached and managed. It also plays a key role in the repair of EBS volume. So when we have storage servers that fail, different volume types have different replication strategies, and the Configuration Manager helps us manage all that. Now, when we created this service, we focused on reducing our dependencies and interactions with other services. And at the time, our availability zones were pretty small, and so we thought about the availability zone as the largest thing that could be impacted by any failure, and thought that was a good blast radius. We knew we needed this service to be available and highly durable because it did control the critical information about your volume. And so we built this on top of Paxos-based replication. We operated this for a little bit, and we were really happy with the improved scaling and blast radius reduction properties of moving it to be an AZ service. So we decided we should move the rest of the control plane. Now, we could have taken that storage manager and stamped out multiples, one for every availability zone. But we took the opportunity to reevaluate our strategy and began to use a service-oriented architecture. This was about 10 years ago, before the term microservices has become really popular, but that's really what we ended up building. We separated the function of storage manager into many smaller services. And this allowed us to be a lot more efficient, not just because we no longer had to scale vertically with giant hardware, but we could think about the individual components that needed to scale and be more independent about that. It wasn't just compute resources, though. We found that our developers also became more efficient. With a service-based architecture, developers can focus on the key components, and they don't have to keep the entire control plane in their head in order to operate and reason about it. Over time, AWS availability zones have grown to tens of data centers. And so as we've scaled and as our customers have scaled their usage, even a configuration manager for a single availability zone was too big. And so we set out to create even smaller boundaries. We asked ourselves, what's the smallest blast radius we could have? And as we were thinking about this question, we coined a new term internally. We call this new thing a cell. A cell is the smallest unit of failure that we think about in AWS. Different services and components have different cell sizes. Makes sense. For the configuration manager, we wanted the cell to be as small as possible. As we were thinking about how small we could make the cell, we made a key observation. Unlike most databases, where you've got thousands or millions of clients that are all trying to get different parts of the data, and you really don't know what's going on and who's going to want what data, we knew that we only had a few clients that needed access to specific data. Specifically, we had the EC2 host and the storage servers and the control plane. The neat thing was we controlled every part, and we recognized that because of this, we could actually create the cell for our configuration manager to be one volume. And so this led to Physalia and millions of tiny databases. The only clients required are really the storage servers, as I mentioned, the EC2 instances. We enjoyed the properties that Paxos gave us, and so we continued to build this on Paxos. Each cell in Physalia is a 7-node cluster, And we can place each one of those nodes near the clients. So we can put it near the volume on the storage servers for both availability and durability. So if there happens to be a network partition, we don't partition off the configuration manager from its volume resources. Now, typically when you build a service, it's kind of small. Maybe you think about a little bit of automation, but you probably don't, because developers, I know I am, can be lazy. But when you're thinking about a volume or a cell for every volume, and millions of these things, you really have to think critically about management. And so when we were building Phasalia, we started with automation as a key foundational principle. And in fact, much of the automation that we built for Phasalia actually was built before we even tested the first cell in production. We design our data plane systems to recover from failure with as little human interaction and control plane interaction as possible. Whether it's a network partition or a larger scale power outage, we built our systems with static stability or the ability to recover to a steady state in mind. And we're continuously improving in this area and our ability to recover more quickly. As with any type of storage, we encourage customers to have a robust, secure backup strategy in place to secure their data. EBS offers a fully managed backup tool with EBS snapshots. Snapshots are point-in-time copies of your data that are stored in Amazon S3. They can be used to restore to an earlier point in time in the event of an incorrect configuration change. You can scale out your service by creating more volumes from that point in time, easily making the replication and catch-up easier. Or you can copy volumes across availability zones. When a new volume is created, you can then choose to create it off of a snapshot. In that scenario, the new volume begins as an exact replica of the original volume at the point in time the snapshot was taken. Snapshots give you immediate access to EBS volume data, and they can also share EBS snapshots with other accounts, other customers, and you can copy them across the AWS regions. Snapshots allow you to have geographic protection of your data, and they also enable you to achieve business continuity for your organization. So let's go through a few of the ways that you can leverage the features of snapshots to improve your operations on EBS. Now, it's always important to keep track of your data. One of the ways that's common throughout most AWS services is the use of tags, and snapshots are no different in this area. You can tag a snapshot at any time, but we recommend that you tag them when you create them so you know what's in them. Oftentimes, customers can use multiple tags to help with things like source, retention policies. EBS snapshots even offer the ability to leverage tags for cost allocation purposes. So you can accurately track snapshot usage, whether it's dev versus test, or maybe business unit or cost center. Additionally, you can create IAM policies based on tagging to restrict access and usage of commands like create snapshot, delete snapshot, and modify snapshot, which is used for sharing and other permission settings. While we're on the topic of security, I'm going to briefly mention this now, and I'll dive in a little bit. If you take a snapshot of an encrypted volume, that data will always remain encrypted. But what about older snapshots that may have been created from an unencrypted source? You can use the copy snapshot functionality to also encrypt a snapshot, either in the same region or when you copy it to a different region for your disaster recovery strategy. Another powerful feature of snapshots that we've seen a lot of customers make use of is sharing. It's a best practice to create AWS accounts that are just for your production workload. And so these accounts should be isolated and follow a pattern of least access. You can have different accounts for your dev workloads, different accounts for your test workloads. With snapshot sharing, you can create snapshots of your production workload and share them carefully, of course, with your dev and test environments. Maybe you want to do load testing, maybe you want to do simulation or other investigations. We've also seen customers use snapshots, and they would build an Omni factory account that creates the golden image that all of their services run on. They then share this with the accounts in their organization. Let's talk a little bit about performance. So what are the target workloads for AWS SAN in the cloud? Well, everything that you run in your on-premises mid-range SAN. These are typically your most demanding applications, and they form the foundation of your business. Things like mission-critical deployments of Oracle, SAP HANA, Microsoft SQL, really anything that requires high durability, high IOPS, and low latency are good candidates. When previously you may have had to stripe multiple IO2 volumes together to get performance, With IO2 Block Express, you can now get the performance on a single volume. Speaking of IOPS, latency, and throughput, these are things we talk about when it comes to performance. But what do they actually mean, and how do you figure out more details about your workload? Well, on Linux, you can use the IOStat tool. I've got an example command here. IOStat actually shows, the very first thing that IOStat shows is the totals since boot. And then this particular command outputs a summary of every 5 seconds after that. Here we can see that the application is driving almost 25,000 reads per second, and a total of 1,000 megabytes per second of throughput. Leads to an average request size of 40 kilobytes. We're doing a small amount of writes, totaling 6 megabytes per second. And these look like 4K writes, and that's about what they are if you do the math. And then over the previous 5 seconds, all the I/O together averages out to 78 sectors. And it's a 512-byte sector, and so it's 39 kilobytes per request. Now, averages are great and all, and they give you a good idea of what's going on, but they don't give you the whole story. Linux has a tool called BlockTrace available. BlockTrace and the accompanying tools to parse and analyze the files give you a much more robust set of information about what the block I/O layer is doing. So you can see when the I/Os are actually queued, when they're completed, and different phases in between. So in this example, running the same workload that I was on the IOStat before, I'm going to leverage BlockTrace to capture 5 minutes of data, parse those out, and then I wrote a quick script that will summarize it for me. It's a pretty simple Python script. Here it is, nothing too exciting about it. It keeps track of a histogram of all I/O sizes, and then it looks at offsets as a really coarse-grained method to determine sequentiality of the I/O. And so if I run this on the previous trace files, you can see here that the workload was mostly random reads. A lot of 16K I/Os, a lot of 64K I/Os, which average out to about 40K. And then on writes, it was almost entirely sequential, with the small 4K I/Os that we saw before. So this looks a lot like what a database would do. You've got random table reads and sequential log write. And by using these tools and looking at a lot of different patterns, I'm able to recognize some of these things. But a lot of things come obvious in how you think about which volume types to choose. When EBS launched 13 years ago, we started with a storage fabric that relied on TCP transport. Now, I won't dive into TCP today, but many technologies are built on top of it. It offers reliable delivery of data, and it handles transitioning between different network speeds, and it can also manage reordering and congestion events. It really is a jack-of-all-trades transport. But that's the problem. It does a lot of things well, but as we scaled our data center networks and EC2 instance and EBS volume performance, we found places where TCP starts to struggle and has difficulty in our environment. When we first launched, an EBS volume was contained on a pair of servers. Today, EBS volumes are sharded across multiple servers with varying replication strategies. One of the challenges of sharding is that when there are simultaneous read requests to the volume, each server can return their data at exactly the same time, causing a microburst in the last mile, or the link between the EC2 host and the switch that it's connected to. More data that link can process, overflowing the link and overflowing any buffers in the network. This is a phenomenon that's called TCP incast. This synchronized congestion causes significant throughput collapse based on the way that the TCP backoff and congestion control algorithms are programmed. Now we can adjust those control algorithms, and we can adjust other properties within our storage fabric, which allowed us to drive throughput higher than we'd originally thought. But really, it just delays the onset of incast. It never really eliminates it. In this and other failures, TCP-based fabrics are typically slower to recover from failure. And additionally, as we think more and more about hardware offloads at AWS, TCP-based protocols tend to require more chip real estate if we want to program them in hardware. So faced with these challenges, we took a step back and started to think about our storage fabric and how we would build a next-generation fabric. First, we took a look at our data center networks. Our data centers are built with a tremendous amount of capacity. They're relatively flat to ensure good latency, and they're built on what we call equal cost multipath, which means that there's multiple links between two endpoints, and so we can quickly and easily route around failure. These paths exist both for capacity and for reliability reasons. Now, as we thought about storage, we recognized that while the data for an I/O needed to arrive in order, so if we segment out that request, that data needs to arrive in order, outstanding IOs could be reordered relative to each other. To ensure data consistency, we already serialized data in our storage durability engines. And because of these, we really don't need the additional serialization built into TCP to ensure data correctness. With these requirements in mind, we started working with a few other teams within AWS and built a next-generation storage fabric on top of SRD. What's SRD? SRD, or Scalable Reliable Datagram, is a transport protocol that incorporates our experience operating extreme workloads at cloud scale, using our large network as an advantage to deliver even higher throughput and lower latency for our customers. In-flight IOs are able to take advantage of multipath capabilities in our network. Each IO can take an individual path through the network, quickly routing around congestion and failure. Because we no longer serialize in the transport, a single bad path won't prevent all IOs from continuing. Any IOs sent on the failed path can quickly be retried on other paths. Now, the congestion control algorithms are also able to consider each IO individually, more quickly responding to and recovering from incast-style events, making them really no longer an issue for us. Of course, the fast healing properties also reduce latency, and critically, latency jitter for your application's IOs. When we introduced the Nitro card for EBS with C4 instances in 2015, we were finally able to offload our storage functions into hardware. In C4, the Nitro card exposed NVMe to the hypervisor, in this case Xen, which then used a paravirtual driver to expose the storage to your guest. One of the reasons we chose this method is because of the stability of NVMe drivers in 2015 wasn't great, and so we wanted to protect customers from that. With this first Nitro controller, we were able to offload all EBS volume encryption in hardware, and that hardware is capable of full-speed encryption. Not only does this improve performance, making encrypted volumes performance equal to unencrypted volumes, but it also improves security. With Nitro encryption, EBS volume keys are no longer in the hypervisor. They're only available to that hardware engine. We're also able to offer EBS optimized by default. EBS optimized is a specific network that's reserved just for storage traffic. Over time, NVMe drivers improved in Linux, BSD, and we also built a custom add-on driver for Windows to improve upon the capabilities of the native driver. In our Nitro-based instances that we launched in 2017, we now expose EBS volumes as a virtualized PCI controller into your instance, removing the hypervisor as a source of jitter from your storage I/O performance. And we listened to the customer feedback, and smaller Nitro instances also offer additional on-demand burst of storage bandwidth, allowing you to select a smaller instance size than you may have needed to before. Each generation of Nitro controller adds additional capabilities and performance. Taking advantage of this, last year we launched the R5B instance family, the first instance designed for high-performance storage-bound workloads. This instance family has the same vCPU to memory ratio as R5, but includes 3 times more EBS performance, up to 260,000 IOPS and 7,500 megabytes per second of throughput. This was the first instance to also take advantage of our new storage fabric, which is one of the foundational components of SAN in the cloud. We expect to bring this fabric to more Nitro instances soon. We launched EBS with a small number of code repositories for the entire service. Our control plane, our storage durability engines, and the other guest software that presented a virtualized block device. I could actually count them on a single hand. When we started moving to a service-based architecture in our control plane, that number expanded greatly. We found that not only were we able to scale more easily, but able to move quicker to add new features and functionality. Recently, we started to wonder if we could be successful applying some of the things that we learned to our high-performance data plane. Now, typically, this is a challenging prospect. If you've operated and built data planes, one of the things that you'll know is that you're really counting cycles, thinking critically about the operations that you're doing in the core fast path. Decoupling, or moving functionality across code boundaries, tends to create overhead due to the requirements of servicing the APIs and the cross-code sharing. As we started exploring, a few things really started to come to light. First, it caused us to think deeply and critically about what needed to be in our core fast path. We wanted only to have the absolute minimum functionality between pulling an I/O off the wire and committing it to durable media. we recognize that over time, as our service has grown, some extra processing had been added to the FastPath that may not have needed to be there. Removing the asynchronous functionality allowed us to build an even tighter durability engine. Second, as we started building, we recognized that not only was our code, and thus our system, faster, we were able to reason more about the correctness and security properties of it. While this isn't a talk about formal methods, and formal methods are something that we use a lot of in AWS, I will point out that if you have smaller code, it's much easier to model your components in tools like TLA Plus or P if they're more compact. This leads to more trust in your algorithms. When you're able to define APIs between functionality, it's easier to have teams focus on the code within that API boundary, similar to what we've seen in control planes. The result of this effort is what we call Block Express, which we launched in preview at re:Invent last year and generally available a few months ago. As we were building Block Express, we took the opportunity to reevaluate our hardware designs and take advantage of our scale, our agility, and our new development methodologies to deliver a more consistent and higher performance EBS storage engine. If you were paying attention this morning, we launched i4 instances with Nitro SSD. Block Express has been using Nitro SSD as well, and it's one of the things that if you want to learn more about, Peter DeSantis is going to talk about tomorrow in his keynote. The question is, how much more consistent did this work make it? Well, let me show you. I did a comparison of two volumes, IO1, which is on our previous generation architecture, and IO2 on Block Express. I connected them to the same instance and ran a FIO workload, 16K write workload on both of them. This graph is a cumulative distribution function. On the left-hand side of the graph is the minimum observed latency. And as you can see from the instance, or as it's seen from the instance, and that latency is in microseconds. Even at the lowest end, we're already seeing the benefits of IO2 Block Express. As we move over to the right into the higher percentiles, the IO1 volume has a higher slope, or increasing latencies when compared to the IO2 Block Express. The knee, or where the slope dramatically changes, is also at a lower percentile value than the Block Express volume. IO2 Block Express maintains a sub-millisecond latency well into those high percentiles. IO2 Block Express, together with R5B instances and our SRD-based storage fabric, give you the performance of a SAN in the cloud with the power of the AWS pay-as-you-go pricing model without any of the headaches associated with SANs. The most important thing our customers are concerned about is security. EBS prioritizes security first. EBS volumes support encryption of data at rest, data in transit, and all volume backups. It's supported by all volume types, and it's integrated with AWS KMS infrastructure. And with our investment in the Nitro architecture, like I mentioned, there will be no impact on performance to your volume. And recently, we announced several new encryption enhancement features, allowing you to encrypt all new volumes created in your account with a single opt-in setting, greatly simplifying your internal security compliance programs. So how does encryption work? Well, you can choose either the default key for the KMS customer master key or a custom customer master key to protect your data. Once the volume's enabled for encryption, all data on that volume is encrypted. We encrypt right next to the instance and the hardware powering your instance. And then that encryption remains over the network wire and on our storage servers, and then of course, any snapshots that you take from that. And any volumes created from those snapshots also retain those encryption policies. Now, if you build encryption within the instance instead of relying on EBS encryption, some of the CPU that powers your instance will be dedicated to encryption. If you use EBS encryption instead, we offload that into the Nitro hardware. So there's not going to be any performance impact. And this is true for all Nitro instances and a lot of our previous generation as well. It's easy to specify volume encryption when you create the volume. Just check the box for encrypt this volume. As part of create, you can choose to use the default key or select another master key within your account. Using a custom master key, it gives you the ability to further audit access and control things like key rotation and access policies. What if you want to ensure all of your volumes in your account remain encrypted? Well, you could create IAM policies that restrict creation of unencrypted volumes. Combine those with config rules that detect an alarm on unencrypted volumes. But really, that's a lot of work. Recently, we launched the ability to enable encryption of all new EBS volumes by default. This is an account level regional setting. This also allows you to keep your same workloads that you're used to now and easily migrate to EBS volume encryption. To set it up, all you have to do is go into your EC2 dashboard, select EBS encryption under the account attributes. Now, like I said, this is a regional setting, and for this account, it's currently disabled in our Ohio region. After clicking Manage, you can select the Always Encrypt New EBS volume, as well as choose the key that you want to do, whether it's the default key or a custom key. Once you've updated the policy, the new volume, any new volume created in that account will default to encryption with the selected key. Of course, if you want to specify a different key, maybe you want to change to a different custom CMK for some of your volumes, you can do that when you create the volume. Data security is important. We didn't really talk a lot about snapshots. There's a few other sessions this year at reInvent about them. But it's important to remember that snapshots can be shared. You want to keep track of which snapshots are shared and why. You can leverage tags to help you if you want. And really, you want to ensure that account-level volume encryption is enabled. So as we come to the end of our session, hopefully it's clear a lot of the things that we've done to build SAN in the cloud are directly targeted at the key things our customers are asking for. We continue to lower cost for customers with volumes like GP3, drive higher performance and reliability for our volumes with IO2 and IO2 Block Express. We continue to improve the ability of customers to scale and manage their EBS resources with features like elastic volumes and fast snapshot restore. And then we continue to make it simpler to use and manage EBS securely with features like account level volume encryption. And with that, I hope you enjoy the rest of your week at reInvent. Thanks.